Okay, we are recording. This is Unit 1, Progress Check, Open Response Question. And the question is about an object that rolls down an inclined plane, and the incline is slightly less than 1 meter in length. A group of students wants to determine the acceleration of the object while it's rolling down the incline, and they have access to the following equipment: a stopwatch, a clock, a meter stick, a pair of calipers. Okay, right off the bat, the clock can measure up to 12 hours. I don't think this thing's going to take 12 hours to roll down a 1 meter incline. And it's got a precision of 1 minute. In fact, this is not going to take 1 minute to roll down a 1 meter incline. So the clock, the clock is useful to us. Calipers, I don't know, if you want, calipers are used to measure really small things, like the thickness of a thin sheet of metal or the thickness of a wire, right? So a pair of dial calipers isn't going to really do us any good either. We are interested in the stopwatch and the meter stick. But so assume the object moves with a constant acceleration as it rolls down the incline. Write an equation that includes acceleration and quantities that can be measured from measurements by using the available. Is somebody trying to ask me a question? I hear some breaking up audio, and I'm not sure if somebody's trying to ask me a question. Be loud and clear if you are, and be persistent. I might be hearing reverb too. Okay, listen guys. So the first thing you do is you say to yourself, self, what kind of motion is this? Is it constant motion, or is it accelerated motion? Which one?
Accelerated.
Clearly accelerated motion. And so you go to your equation sheet and you have a few equations. You have V equals V plus AT. You have X equals V initial, I go with the subscript again, V initial T plus 1/2 AT squared. And there's another one, V squared is V naught squared plus 2A delta X. But we don't need. Do either of these speak to this? I mean, they both do. But which one would you use if you want to measure stuff easily?
First one.
Well, but you're going to have a hard time. Well, I guess you could. I mean, you could find the velocity down here.
I used the second one.
Yeah,
I used the second one because the velocity is kind of irrelevant if it starts from rest.
Right. So listen, if it starts from rest, then our formula is 1/2 AT squared. And remember, we're interested in finding the acceleration. We're interested in finding A. So you ask yourself, with the equipment that you have available, can you measure displacement and time? And the answer is yes. You've got a meter stick and a stopwatch. Okay. So boom, my answer to A is right here. Here's my answer to A. Write down an equation right here. There. I just got full credit for part A. You just have to find the right equation. You decide, look, this is what you have, a meter stick and a stopwatch. You know, I think that was Andre was saying, I'm not quite sure, but I think Andre was saying you could use the first one. And so V initial is 0.
That's how I do it.
And so you could, and what you would do, Andre, is
we don't have to say anything.
You would have to find the final velocity, because that's final velocity right there. But you could put a piece of tape here and measure its approximate final velocity, right? You could like, oh, it took 2 seconds to go 20 centimeters, and 2 over 0.2 is whatever. 2 over 0.2 is 10, right? Meters per second. Obviously, that's not going to be that fast, but you could get a final velocity here pretty readily with this equipment and solve for acceleration that way too. Okay? I think either one of these would work. I think this one is going to get better results because Well, just because I know these people and I know they're going to ask me to graph things. And so if I use this, I can put increments down here and get lots of data, right? 10 centimeters, 20 centimeters, 30 centimeters, 40 centimeters. I can make little marks, 50, 60, so on and so forth, and get time all the way down to each mark, right? In either case, just go with it and then decide what you're going to measure.
I have a quick question.
Well, yes, who's that? Yes, go right ahead.
Mr. Warren, so for that, yes, me, sorry. So you put it in the form x equals 1/2 he squared. For it to be like, you don't have to put it in like a equals. You put that.
You don't have to solve it for that yet. Nope, you just have to identify
Okay.
an equation.
Okay.
Right,
Thank you.
good. So quantity to be measured, well, we're going to measure some displacements. And the symbol for displacement is x, and the equipment is the meter stick. Okay. What else am I going to measure? How long it takes. I'm just going to, oops, I keep doing that. I'm going to measure how long it takes also. I'm going to measure how long it takes, so time. And symbol for time is t. And I'm going to use the stopwatch, not the clock. Don't use the clock. The clock's only good to a minute. I need to measure displacement. That's all I need to measure, x and t. Am I sure? Yeah, I need to measure x and t. And I'm good to go. So describe the overall procedure. Well, Andre and I just came up with one method. I'm going to speak of a different method here. I would say using the meter stick, oh, it's two words, right? Sorry. Using the meter stick, mark every 20 centimeters. Mark every 20 centimeters. Release the ball, it's a cylinder, sorry. Release the cylinder from the top and measure the amount of time it takes to get to the 20 centimeter, what did I say, 40 centimeter, 60 centimeter, 80 centimeter, and 100 centimeter mark. Okay. Describe the overall procedure. Using the meter stick, mark every 20 centimeters, I guess probably say every 20 centimeters where down the ramp. Provide enough details so another student can replicate, including steps necessary to reduce experimental uncertainty. Repeat, experiment. They love the number 5. Repeat the experiment. Okay. Reduce experimental as needed. Use the symbols defined or table to include simple diagrams. I think that's pretty clear. I'm going quick here. You could be a little bit more thorough, but I think it's pretty clear what I'm going to do. I'm going to see how long it takes to go 20 centimeters, and I'm going to write it down. I'm going to see how long it takes to go 40 and 60 and 80 centimeters and 100 centimeters. And I'm going to write it down, and I'm going to do it a handful of times just to make sure nothing weird happened with any given trial. What can be graphed to yield a straight line? Well, gosh, I don't know. Same rigmarole as before we just saw in the other class. Let's see where I'm at here. Boom, boom. You want a graph, and you want it to be linear. So here's an x and a y coordinate, and you want the graph of this thing's motion. It's accelerated motion, but you want the graph to be linear. It says right here to yield a straight line that can be used to determine the acceleration. So. Do I still have, whoops. Do I still have that equation in my clipboard? Let's see. Yes. Okay, well, look at this. Look at this. Acceleration, let's just solve this for a quick acceleration. Dea was just asking about this. Acceleration is 2x over t squared. Okay. Look, guys, acceleration is going to be 2x over t squared. If you graph rise over run, you're good to go. you could graph 2x here and t squared here. And if you graphed 2x over t squared, you would have the slope of this line would be rise over run. The slope of this line is rise, 2x, over run, t squared, and 2x over t squared is the acceleration. So if you vertical axis, 2x, horizontal axis, t squared. How could graph be used to analyze to determine the acceleration? And I would just write, if one were to graph 2x over t squared, the slope of the line would be the value of the acceleration. Singular. And I spelled it wrong. Okay, so it sounds kind of confusing when you read this stuff, but really, is the solution terribly complicated? I'm really just getting information from the appropriate kinematic equation, which they really kind of helped me pull out of my head here. They kind of helped me pull it out of my hat right here, and using that equation, if I want A, just solve the equation for A. And if it's in the format of, something divided by something else, well then, that's that. If you graph that to that, that's the slope. That's the rise over the run, right? So you're off and running on this one. Now, if you read this carefully, you're going to get the answer without even really doing any math. After rolling down the incline, the cylindrical object rolls across this horizontal surface, as shown above. It then hits a vertical wall and bounces off the wall. So it's rolling, it hits the wall, and it bounces off the wall with the same speed it had before. Okay, not likely, but whatever. It makes the math easy. It bounces off the wall with the same speed it had before. Note that during the bounce, the object is in contact with the wall for a time interval that is very small, but not zero. Okay, now let me ask you this. This thing went from 0 to some speed in some relatively large amount of time, right? It accelerated down the ramp. It went from 0 to some speed in some, whether it was 3 seconds or 5 or 7 seconds, we don't really know, but presumably some number of seconds it rolled down this ramp. It hits the wall and bounces back for a very short time period, but not 0, okay? So listen, this thing, let's just give this easy to think about numbers. Let's say it went from 0 to 2 meters per second, okay? Then the acceleration was 2 meters per second faster in, let's just say it was on the ramp for 2 seconds, right? If it went 2 meters per second faster in a 2-second period, then the acceleration would be 1 meter per second squared, right? Now look, guys, then it's going 2 meters a second, it's going 2 meters a second, it's going 2 meters a second. Bam, it hits the wall. It's going the other way 2 meters a second. What was the delta V there, the change in velocity? It went from 2 to -2.
4.
Yeah. The change in velocity was 4 meters per second in a very short time period. On the dot below, which represents the object during the time it is in contact with the wall, draw an arrow showing the direction of the object's acceleration. What should I draw here, guys?
So it's inelastic.
Well, wait a second. Let me just do this here. Boom, boom, line style. Okay. Wait. Alex, was that you?
Yeah.
And you said it's inelastic?
Mm-hmm.
But it's not. It's elastic because it says it bounces off with the same speed it hit at. Right? It says it right here. Let's see. Bounces off the wall with the same speed it had before. So it's elastic. All KE is conserved. Whatever amount of KE it has here, it has the same quantity of KE here. It has the same velocity. right? So that makes it
Oh,
elastic.
I mixed up the words then.
Okay, yeah. That's a perfectly elastic collision. That's why I said a moment ago, not likely, but they're setting the stage here, so fine, makes it easier on us. But while it's right here, what is the direction of the acceleration? And if you're confused about that, acceleration, of course, is always in direction of the force. Is this ball being pushed on? And if so, in which direction?
Both
Opposite.
directions. Because of the normal force and the acceleration downward.
Wait, so which direction is this ball being pushed? Right here.
Oh wait, it's only the normal force because it's going at a constant velocity. Yeah.
Say again? Which way?
Left.
Left. That ball is being pushed that way. It hit the wall. If the ball pushes the wall to the right, the wall pushes the ball to the left. That's why it goes back the other way. So that's my answer right here. Boom. On the dot below, while in contact with the wall, draw an arrow showing the direction of the object's acceleration during the bounce. It's, there are forces up by the floor or whatever this is, the table. There are forces down due to the Earth's gravitation, but they're not saying that. They're saying, draw an arrow showing the direction of the object's acceleration during the bounce. The acceleration, while it's hitting the wall, the acceleration is in the direction of the net force. It's changing its velocity from a rightward velocity to a leftward velocity. So the acceleration and the force is to the left. Okay. Now, this is very important. During the time the object is in contact with the wall, is the magnitude of the acceleration greater than, less than, or the same while it was rolling down the ramp? When did it have a bigger acceleration? When it was accelerating down the ramp, or when it was bouncing off the wall? When did it have a larger acceleration?
Bouncing off the wall because the rate of acceleration was a lot faster than when it was rolling down the ramp.
Yeah, and how do you know the rate of acceleration is larger? You're right.
It says note that during the bounce of the object, it's contact with the wall first time interval that is very small but not zero, and it's saying that it bounced back with the same speed that it bounced towards it.
Yeah.
So it went the same. It accumulated the same.
Yeah. Good, Andre. Right. So Andre is recognizing this. Down the ramp, it gets up to some speed. Right. So it goes, maybe 2 meters a second faster, just as a maybe it's 2 meters per second faster, and maybe that took 1 second just to come up with some numbers, right? And so that would be 2 meters per second squared of acceleration. But when it's bouncing off the wall, a couple people just said the change of velocity is 4 meters per second in a very short time period. So I don't know, 0.1, right? So this is more like 40. I mean, if these are the real numbers, but there's a larger acceleration when it's hitting the wall because A, there's a bigger velocity change, and B, it happens in a lesser time period, right? Here, the velocity change is from 0 to say 2. And then here, it's twice that because it bounces off the wall and goes back the other direction at the same exact speed it was going originally, right? So that's right, Andre. During the time the object's in contact, what was the greater than, less than, or the same? The answer here is greater than. And then it's going to say justify or prove it. They always say prove it. And so you would make this argument I just made, right? Greater than. Sorry about that. Right? Because the velocity, the change in velocity while rolling down the ramp was lesser than bouncing off the wall and took more time. The wall, and then say clearly, the wall provided a larger acceleration. Okay. Oh. Any questions? Next one. Okay. This one is going to be a little bit easier. Hope you had a chance to take a look at it. It's an astronaut on planet X. An astronaut holds a rock 100 meters above the surface of planet X. The rock is then thrown upward with a speed of 15 meters per second. Nice throw, astronaut, as shown in the figure. The rock reaches the ground 10 seconds after it's thrown, and the atmosphere of X has negligible effect on the rock when it's in free fall. So don't worry about air friction, okay? You know what I would do? I would do what I like to do, which is make my lists. So I know that V initial is positive 15 meters per second. Okay. I don't know what V final is. I don't know what V final is. I know that it says it hits the ground 10 seconds later. I know that the displacement, Y, delta Y. Now listen, other people in the other class get confused about this. The displacement of this rock is negative 100 meters. Okay? We're not talking distance. We're not talking how high it goes up, total distance traveled, and how far it goes down. We're not talking distance. We're talking how far it ends up from where it started, right? That's displacement. It's here, and if we're calling this positive, if we're calling this upward value positive, that means we're treating up as positive and down as negative. Sometimes when I get confused, which is generally only on days that end with Y, I often do stuff like this just to keep my head clear. Positive and negative. Right. So there's my coordinate system. If that's positive, the displacement from here down to here is negative 100. What else do I know? Do I know anything else? Let's see, V, T, planet at 15 meters a second, 10 seconds later. That's all I know, okay? And we're after, what does it say? Determine the acceleration, A. Right? That little list is gonna help me a lot, it really is. Because first of all, just like the previous motion problem, I'm always gonna start like this. I'm going to say to myself, is this positive or is this constant or is this accelerated motion? And this is clearly a case of accelerated motion. That's why they're asking what the acceleration is. And so I go to my list of equations, which you know is V equals V naught plus AT, right? There's one of my equations. I've got another equation that says Y equals V naught T, V naught, oh boy, here we go. T, yep, still subscripted. V naught T, oh boy. V naught T, this is the painful part, watching me try to type, sorry guys, plus 1/2 AT squared, right? And we have another one that doesn't involve time at all. And guess which equation I'm going to use here? Uh-oh, are you guys still there?
The second one.
A few, yeah, the second one, right? So I'm after A. I have displacement, I have initial velocity, I have time. That's just a number, 0.5. There's A, which is what I'm after, and there's T. Oh, okay. Well, so what's the acceleration on this planet? A equals, let's see here, let's multiply by, let's go like this. 2, let's multiply everything by 2. 2y, let's do 2 y, let's see, where am I here? Y minus V naught T y minus V naught T, yeah, and I've got to divide by T squared, and so this is over T squared. That's a 2, sorry, not a Z. You can do this in your head. Y minus V naught T. Okay, well, let's get V naught T. So V naught T is 15 times 10, do you agree? 150, right? So Y minus V naught T is 100 minus 150. Does anybody know what 100 minus 150 is? Of course you do. 100, I can't hear you too well, but 100 minus, I know you know the answer. 100 minus 150 is 250, and 2 times 250 is 500. So I've got 500 over t squared here, and t is 10. 500 over 10 squared is 500 over 100. My answer to A is 500 over 100. My acceleration is 500 over 100 is 5 meters per second squared. Okay? That is a very straightforward kinematics problem, and it was my list right here. It was my list right here that drove, whoa. It was my list right here that drove really my thinking and my process. Right? My simple little list got me the answer, and it would have been quick if I didn't have to, type it in this format. It would have been a lot faster. How does the speed of the rock when it reaches the ground compare to the speed of the rock when it's thrown upward? Anybody want to take a stab at that? How's this velocity down here compared to the velocity of 15?
65 when it reaches the ground.
I can't hear you. Say again.
It's going 65 when it reaches the ground.
Okay, and only 15 up top, right? So you would say the speed when it reaches the ground compared to the speed when it's thrown upward, the velocity downward is greater than the velocity upward. Would you say that?
Yes.
Velocity down equals, velocity down is less than. No, yeah, it's the first one, right? State your reasoning. Well, you can just say, the rock was thrown straight up at 15 meters a second, and when it passed the astronaut on its way down, it passed him, her, whatever. It passed him or her. The rock was thrown straight up at 15, and when it passed the astronaut on its way down, it passed him or her at 15 meters per second and continued to gain speed the whole way down. And if you wanted to, you could put your number in there. That sounded like Andre, or maybe that was Alex. I think it was Andre. But that's the answer. Okay. Now, a student wants to know how the motion of the rock would be different if it was thrown upward at 15 from a height of 100 meters above the Earth's surface. In a clear, coherent paragraph length response, how would the motion of the rock on Earth be different from its motion on planet X in terms of its maximum height, the speed at which it reaches, and the time and the acceleration due to gravity? Right. So taking a look at this, I'm not going to write it all out. I'm sure you can do that quite well. How would this be different on Earth? Right. So time. How would time be different on Earth? Or would it?
The acceleration is 2 times greater, it would take less time to get down, so it would decrease.
Since acceleration is 2 times greater, the flight would be shorter in time. Yes. How about what did it say? Max displacement? No. It's what else do they want to know about here? They want to know maximum height and speed. We just did time. Yeah. So maximum height and speed, really. So what about max height on Earth? When he throws it up, or shoot, here they throw it up, the maximum height on Earth, what would happen?
Again, since the acceleration on Earth are 2 times greater, it wouldn't reach the same height because it'd be pulled down.
I couldn't quite hear you. It would not go as high, right? If you
Yeah.
threw something up at 10 meters a second or whatever, 15 meters a second on Earth, it would go to some height. But if you did that on Jupiter, it would go less high. And if you did that on the moon, it would go higher, right? So it's going to go higher if there's less gravity. And it's going to go less high if there's more gravity. And the other one was the speed at which it hits the ground. V down, they called it. The speed with which it hits the ground. Would it be greater on Earth, lesser on Earth, same on Earth? Keep running with the same thought process.
It'd be running faster since it's acceleration is 2 times greater, so it'd be accelerating towards the Earth 2 times faster.
Yeah. Okay. So you would just say something like this. Just think clearly and write simple stuff. Don't get crazy and use big crazy words. Just be simple and clear. Okay. That's the astronaut problem. Okay. I'm going to stop recording.